Hi everybody, hope you're doing well. This is a lecture following the previous one where we talked about spin precession, but the magnetic field at that time was a static magnetic field, and now we want to generalize in general, for quantum dynamics of two-level systems. It's a very important problem in quantum mechanics. Four or more recipients of Nobel Prize in physics worked with two-level systems. Just to mention a few: Isidore Rabi, which discussed and worked with molecular beams and nuclear magnetic resonance; uh, Basov, Prokhorov, and Taunes, which discovered experimentally the Maser effect. All right, so it's a very important technological development in physics for atomic clocks and all that. And the difference between the Maser and the laser is just the electromagnetic spectrum. Masers are amplification of electromagnetic waves by stimulated emissions, but in the microwave domain, while lasers are in the optical domain. I ask you to excuse me because the shadow here, I didn't solve it properly so far, and I guess in the future I can just adjust a better camera here, so the video will be more presentable, I guess. But for now, that's fine. So, two-level systems can be used to describe masers, two-level lasers, because lasers, there are many models, and many of them are not two-level systems. But for if you can model a laser by two energy levels, then a two-level system can be very well applied. Magnetic resonance, so nuclear magnetic resonance, electron paramagnetic resonance, they are just examples of two-level systems. It's a very, very important issue in quantum mechanics. And I must say that any two-level system, as we will demonstrate in a very easy way, any two-level system can be mapped to a spin half system. All right. So studying the influence of magnetic fields for a spin half particle is just the same problem, mathematically speaking, as any two-level system, because two-level systems can be mapped to a spin half. All right. We skip chapters 3 and 4 is in the book of Sakurai if you want to follow some some textbook here. So Sakurai, go to chapter 5, I guess, page 320, and there he presents the interaction picture for two-level system, discusses the application of two-level systems for masers and all that. But in this case, we will consider the system under the influence of a time-varying stimulus. The difference from the previous lecture was that we were considering there just a constant, a static magnetic field. All right, so we discussed the spin precession. Now we are willing to discuss, we will study the influence of a component of the magnetic field which is time varying. For instance, it can be a radiation, an electromagnetic radiation, radiating the system, the two-level system, and it will induce transitions between the lower and the higher energy state, all right, between the so-called fundamental state to the excited state. So that's it. Well, first consider a very general system. A very general system, it can be written this way: the Hamiltonian for a two-level system, two-level Hamiltonian. It can be written this way. In the language of Dirac's notation, there is an energy, E, all right, E naught, say, which corresponds to state 1. So it's a higher level. It can be the fundamental state, right? So minus E0, the state 1. There are only two states in the system. Plus this E0, I can divide it by 2 here. So it became a symmetric system. The state 2, all right? So you have a system in the energy spectrum with two eigenvalues. This is diagonal. These terms are diagonal. And there are two possible energies, E0 over 2 and minus E0 over 2. This is the zero of energy. You measure in a certain scale of energy. If you do not have a symmetrized problem, you can also perform a symmetrization of the energies. Just take the average and measure the energy levels above and below the average value for the energies. And the energy difference here is delta of E, which corresponds to E0. All right, so the energy difference here is E0. You can symmetrize if this energy value here is not the same in modulus as this other value. All right, so this corresponds to the state 2, and this corresponds to state 1. This is the fundamental state. This is the first excited states, and only these two states play a role in the problem of a two-level system. And it can be an approximation for some systems which have more energy values, but the only accessible states in the system are these two states, all right? So it can be an approximated two-level system, or it can be an exact two-level system. Spin, for instance, is an exact two-level system, all right? So there are also possibilities of transitions between these two states, and we write transitions in off diagonal terms, and I will write a negative value here, a delta, which corresponds to the possibility of jumping from state 2 to the state 1. So if you have a particle here, or the state in an excited state, and an excited level, it can jump to the fundamental state. So this is the fundamental state, and this is the excited state. All right, or ground state. Also, you can talk about the ground state of the system. Ground state means the lowest energy level of the system. There is a notation for, instead of using 1 and 2 for the two-level system, which can mention intuitively these two states, the ground and the excited state. So the ground state is the state 1, and the excited state is the state 2. All right, so that's that's what we can write here. Just make clear that the 1 is the ground state and 2 is the excited state. But I'll use this convention here. Also you can use up state and down state if you are mapping it to spin system. So this is the parallel to the field state, and this is the anti-parallel to the field state if the charge is positive. If you think about an electric charge which has a magnetic momentum with spin half, and you can have only two states in this system. All right, and since the Hamiltonian must be a Hermitian operator, you need to introduce here a complex conjugate of this constant here, and it corresponds to the transition which picks the system from state 1, the fundamental, the ground state, and make it jump to the excited state. All right, so this is the form of the Hamiltonian. All right, this is the general form of a two-level system. All right, I guess you can see clearly what is happening here. This is the energy of fundamental state. This is the energy of the excited state. These two terms here correspond to transitions. So if you want to write a matrix form of this, you will have minus E0 over 2 plus E0 over 2 here in the diagonal. All right, this is the diagonal terms. I guess you can clearly see these values here, and there is a delta. Perhaps I can put a complex conjugate here. So, well, it really doesn't matter. I'll put the complex conjugate here as as we did at first. So this term here is minus delta, and this is minus the complex conjugate of that value. So this matrix, when you just take the transpose conjugated of this matrix, it is Hermitian because it's needed in quantum mechanics. Any system must be Hermitian in quantum mechanics, all right? So this is the matrix. And notice right now, let me just use this form here and rewrite the deltas in the following way. So consider delta to be a number, say a gamma real plus a gamma imaginary, all right, or minus here, it doesn't matter, say plus there. So this is a complex number, and the complex conjugate here corresponds to the real part minus I, the imaginary part of this delta term here. So this is the form of a complex number, this delta. It has units of energy. It has a real part and an imaginary part. That's okay to be a complex number because it is off diagonal. When you diagonalize this matrix here, when you find the eigenvalues of this matrix here, that's an interesting problem. Suppose delta is constant. It's a constant in time. You can find the eigenvalues and eigenvectors. All right. So this is an interesting problem. You can find the eigenvalues and the eigenvectors of this matrix here. It's pretty simple to do that. So I will left it as an exercise. Right. That's a very interesting exercise. But for now, I can just rewrite the Hamiltonian. I guess you can follow me on this as minus E0 over 2, right? So far we never mentioned the Pauli matrices here, but look that if you consider just the diagonal terms here, you can write it as 1 and minus 1 here. So if you put this term in front of this matrix, this is just the Pauli matrix sigma z, all right? Plus or minus the delta, but I'll rewrite here it as the real part minus the imaginary part, and I'll write here the real part, but this has a changed sign, plus I gamma imaginary here. So you can see you can separate the imaginary and real parts of delta. So gamma r multiplies 0, 1, 1, 0, and the imaginary part, which let me change sign just to make things more beautiful here. So in mathematical sense, so I'll put the definition of delta with a minus here, so this changes here and changes here. All right. So that is the complex conjugate, which corresponds to gamma real plus imaginary gamma imaginary, the imaginary part. These numbers, gamma r and gamma I, are reals, right? They are real numbers. And you can write now minus this gamma times 0, this imaginary gamma, minus I, the imaginary here, and 0 here, all right? So you can check that this matrix, if you add up all these things here, this matrix just produces this result here, all right? So uh, this is this matrix here. This matrix here is sigma z. This is sigma x, and this is sigma y. All right. So this problem can be well properly written as something like Hamiltonian, can be written as some minus value, some pseudo-magnetic field, a Pauli matrix vector, a vector of Pauli matrices, dot with B. All right. So this B is just, in this case, this B vector, in this case, for a given arbitrary two-level system, just corresponds here to E0. The X component is gamma R. The imaginary here of the delta is just the Y component, and the Z component is E0 over 2. So you just mapped your two-level system to a spin system. Also, you could put some constant here, some general constant here. If you insert some constant, you can just divide all these terms here by that constant, and that's it. You just written your two-level problem as a spin half system. So two-level problem is mapped as we just consider at first, can be mapped to a spin half system. All right, or two-level system, spin half, they are just the same thing. All right, so we just demonstrated that. Well, now let us talk about some physical situations where a two-level system um, emerges. And consider first a maser. Well, A maser is a microwave amplification by stimulated emission of radiation. A laser is just the replacement of this M here for microwave by L for light. And the distinction laser here, the distinction as this L is light is just the frequency domain. So lasers operate in the optical domain, infrared, visible, ultraviolet spectrum, and also there are X-ray lasers now. So this corresponds to photons with energy of the photon higher than, say, milli electron volts. If you're dealing with the very far infrared region, but for visible light, this corresponds to in the range of 2 electron volts. Ultraviolet, it's in the range of tens to hundreds of electron volts, and X-rays, so this tends to hundreds electron volts, and X-rays higher energies higher than 100 kilo, or perhaps depends on what you define as a X-ray, the frequency spectrum for X-rays, but ranges in kilo electron volts, right? While the infrared here is in the range of some milli electron volts to some electron volts, 1 electron volt, in the range of 1 electron volt for the photon. So the photon here is the delta of E in the two-level system. So you can tune the system to have a difference in the two levels, which can be stimulated, or it can be just modify. You can put modifications. You can insert radiation, so the system can produce transitions between the lowest level and the highest level. And this energy difference, which for a two-level system we call E0, corresponds to the photon you need to insert into the system. And this photon has energies here from 1 milli electron volts and beyond for lasers, for the definition of lasers. And masers, if you want to call a maser something related to the energy of the photon, so masers corresponds to photon energies lower than 1 milli electron volts. So the first maser produced used a ammonia molecule which composed of 3 hydrogen atoms and 1 nitrogen atom, and this has a resonance around something like, I guess, 24 gigahertz, and this was the first maser. But there are masers now using hydrogen or water vapor. There are astronomical sources of maser radiation, and this is a very interesting problem. The ammonia molecule was the first being used to produce maser, all right? And you can calculate here, you just need to calculate the omega, is 2 pi multiplying this frequency in hertz, and you can calculate the energy of the photon by multiplying with Planck's constant. You'll find out what is the energy of the photon, but it's in the range of micro electron volts. All right, it's in the range of micro electron volts. The first maser, just to say a little bit more about the maser, the first was uh, was built considering a molecular beam of ammonia molecules, right? This beam was polarized by an electric field region, and they passed. They were made to go through a cavity. So there is a cavity here somewhere, a cavity, resonant cavity. It's just a box, a metallic box with the frequency properly, the dimensions of the cavity properly projected just to resonate at the difference of two levels for the ammonia molecule. One level is called symmetric state, and the other is the anti-symmetric state. There are two levels. This energy difference between these two states, when submitted to a constant electric field, you split the states of these two things here. The ammonia molecule is a polar molecule, so it has an electric dipole moment, and this, which is the energy difference, corresponds to something in the microwave domain. You can set exactly the difference by applying static electric fields. And when the beam go through the cavity, it is in a higher energy level. When it passes through the cavity, it emits a photon, and it has no time to reabsorb that photon, and it goes out to the cavity, so it recirculates. All right, it's performed at very low temperatures, but around 2018, I guess, and perhaps earlier, the temperatures of operating masers increased, and right now we have maser devices operating at room temperature. All right, so it's very difficult to obtain a coherent radiation, and temperature plays against it. But right now there are masers operating at the room temperature. You can find out. Okay, so that's it for masers. Just corresponds to molecular beam of ammonia. There is an electric field which polarizes the molecules, and some molecules are at a higher energy state when they enter a resonant cavity in the microwave domain. So it has the dimensions. You need to calculate properly the dimensions of the cavity. And when this beam enters a cavity, molecules, by quantum fluctuations here at first, molecules emit photons. And when one molecule emits a photon, it leaves the molecule leaves the cavity, leaving there inside the cavity one photon. And the next molecule, when passing through the cavity, will be stimulated to emit also a photon, and another photon is emitted. So in the steady state, you need to consider some absorptions here, but in the steady state, the number of photons at the proper energy difference increases inside the cavity, and the beam leaves the cavity. It enters in a higher state, leaves in the lower state, and it's polarized again and enters again. This is performed, as I said previously, at very low temperatures for the ammonia beam. And this was developed by Towns, and which is a British scientist, and two Russians, Prokhorov and Basov. It's a two-level system. It is the precursor of the lasers, and they earned the Nobel Prize. I don't remember what year, but they were nominated and they accepted the Nobel Prize in physics, right? So using molecular beams, but also working with nuclear magnetic resonance, Rabi also received the Nobel Prize. I guess in the book of Sakurai, he mentioned that as a footnote in the page 322, 25. You can find in the book, but he mentions that at least four Nobel Prizes were awarded to some people working with two-level systems, molecular beams, lasers, optical things. Another recipient for a Nobel Prize working with systems, but I guess with nuclear magnetic resonance was Felix Bloch, which is a very important name in physics, right? But there are others. Well, that's it for ammonia molecule. The problem in reality corresponds to a Hamiltonian, which is the following form. You have a constant, which depends on some effective electric charge. It corresponds to some electric dipole here, the distance between some positive and negative charge, which is induced by electric fields, but also the molecule is already polarized. Ammonia is a polar molecule, not the electric field. So, and this operator here, which corresponds to electric dipole moment, is mapped to a Pauli matrix times some constant here, and this is just a effectively minus sign here. Effectively, this is a two-level system, but in place of the magnetic moment for a spin, a true spin half system, you insert here an electric dipole moment, and in place of the magnetic field for a true spin system, you must consider the electric field. All right, so this is for the lasers, for the ammonia laser. All right, well, let us now consider effectively the problem which we want to solve. So I will use the language of magnetic fields and spins. So the Hamiltonian, the problem is this one. Hamiltonian is equal to some Bohr magneton, which corresponds to another constant of with another unit if it's a general two-level system where you can map here as we have shown, and the Pauli matrices dot with the magnetic field. All right, so when you are dealing with general systems, general two-level systems, this magnetic field is called pseudomagnetic field. I remember right now that another example where you can map your problem to effectively to a two-level system is a collection of two-level systems, to be precise, is superconductivity. There is a formulation of the problem of superconductivity where you map your problem to spin halves, but it is a combination of of systems of spin half. All right, so superconductivity also can be mapped to spin half problems. All right, but there is a summation of two I guess the Hamiltonian looks like something like this. Some energies depending on some wave number here, and the Pauli matrices dot some some pseudo magnetic field. It's not a magnetic field here. It's related to the gap between the normal state and the ground state, which is a superconducting state. And this depends on the wave vector of electrons. I guess there is a minus sign here. So this is a collection for each k value. You have the Pauli matrices associated with that system. But there's another problem, right? Uh, the formulation is due to Degen. I guess this way which is written. It is also a Nobel Prize winner, right? But the problem is this one here. It's just the Hamiltonian for a spin half system. Spin half system. Spin one half. What is the difference from the previous lecture? Right now, we want to make this magnetic field looks like this one. There is a constant magnetic field along the z-axis, which we can call it a quantization axis. So it splits the up and down states in energy levels. They are separated, they are splitted. You remove the degeneracy of spins because if you don't have any magnetic field, spin up and spin down has the same energy, all right? But when you apply a magnetic field, you break the isotropy of space. There is a preferential space direction, which is the z-axis, because the magnetic field is applied at that direction, and spins tends to align to that direction. So there is a constant magnetic field. This is a constant field or a DC field, all right, or a static field, plus some time varying field, some B, all right? That's the problem we want to solve. So this is usually a time varying stimulus. Usually it corresponds to some radiation field. Okay, this is the radiation field. And typically the modulus of this B field is smaller, orders of magnitude lower than this B0 here, which I am assuming it's positive for the sake of simplicity. All right, so it's positive number. All right, so the B0 here is positive. I hope you can see what I'm writing here. All right, but this number is positive. It doesn't matter. The constant field is very it's more intense than the time varying field. So for instance, it can be used to describe nuclear magnetic resonance. For consider for example nuclear magnetic resonance. Typically this B field, which is static, corresponds to fields in the range of Teslas, and you must know that the 1 Tesla is a very high magnetic field. It's a huge magnetic field. And the modulus of the radiation field of the B field is in the range of millitesla. Very high field for radiation field applied to a NMR system, nuclear magnetic resonance system. All right? I guess you know about the MRI tomography, magnetic resonance imaging, which is used for medical purposes. So they try to use the highest possible magnetic field for making images and for making a tomography. And right now, using superconducting coils, they can get fields as high as 3 or 4 Tesla. But usually, the machines in an MRI machine is around 1, 1.5, 2 Tesla. This is a very huge field. Just to know more about magnetic fields, the more the highest magnetic field, static magnetic field, which was produced by a machine on Earth, was 800 Tesla. All right, this is the highest magnetic field, and the Earth B field is in the range of, in modulus, right? The modulus of this field is in the range of 50 microteslas. All right. So when you insert a magnetic needle to make a compass, uh, you immerse this on a magnetic field in the range of Earth magnetic field. It will align to the Earth magnetic field, to the direction of the Earth magnetic field. But easily with neodymium or uh, any permanent magnet you can find elsewhere in the commerce will produce fields have orders of magnitude higher than this value here. 100 millitesla or 200 millitesla, but near the surface. When you just take some distance from the magnet, the magnetic field of the small magnet drops, and the dependence is at least with the square of the distance, 1 over the square of the distance, or higher dependence. But the problem we want to solve is this one. All right. So there is a constant magnetic field. It is more intense, and there is a time varying magnetic field right here. Right. So we will specify some possibilities. Right. There are two possibilities: linear polarization, which I will use in these lectures because it allows us to make some approximations which are very important in many systems, and you will see what happens. And there is a circular polarization, right? And in this case, this B field, I forgot to mention that this field is perpendicular. It is assumed to be, well, you could put some longitudinal component or some component in the z-axis, but usually this is perpendicular to the z component. So we are wanting to insert transverse fields, right? So there is a direction for the polarizing field. This constant field polarizes the spins, all right? This is in the z direction. and you put the time varying field, which is oscillates in general. It oscillates. I'm representing the oscillation by these two arrows here, which is transverse. All right, so this is perpendicular to the direction of the polarizing field, the constant field. And this, for a linear polarization, I can use, for instance, as the reference axis, the x-axis. I can write it as some b0 cosine of omega 1 t, or just omega t, right? The frequency of the radiation field is omega 0. I'll call it omega 0 in the x direction. Of course, you can choose, this is one possibility. Another possibility for linear polarization would be some b0, the sine of, or the cosine of omega t in the y direction. And any linear combinations of things like this, you could also insert a general phase here, but it doesn't matter for now. This is a linear polarization. A circularly polarized radiation would correspond to a magnitude which is the same for both the x and the y axis. We will choose this. We will choose this for linear polarization and for our stimulus, just to make the calculations, right? So we will use this. But also you can insert some fields which corresponds to this omega t in the x direction, plus or minus the same amplitude sine function of omega t in the y direction. This would correspond to a circularly polarized light or a microwave field, right? Why we don't need to worry about position dependence of the field of the applied radiation. We know that electromagnetic waves, a B field for a magnetic wave, electromagnetic wave would be given by some B0. Suppose it must be real, because here I am writing it as real. It corresponds to something like the real part of some, in this case, some vector which corresponds to a of x plus minus the imaginary a of y. All right, the real part of this exponential of minus I omega t minus some, suppose it's propagating in the z direction. So the direction of propagation of this radiation comes from here, from this axis. All right, the field oscillates in the x direction and the y direction, but it propagates in the z direction. You already know that electromagnetic waves, plane waves, are transverse, so they propagate in some direction and the fields oscillate in the perpendicular direction. So you apply the constant magnetic field and the radiation is inserted propagating in that direction, but with the fields oscillating perpendicular to that direction, so it could have a partial dependence. But the system is so small, the spins are in some particles, the particles are elementary eventually, and this term here, this k here, corresponds to the wave number, which is 2 pi over lambda, this k here, and this lambda here corresponds to wavelength. The wavelength of microwaves are in the range of centimeters, 1 centimeter, 10 centimeters, and the lowest value for this lambda in the microwave domain, if you are concerned with the microwave domain, is in the range of millimeters, 1 millimeter for the upper bound of the radio frequencies, which corresponds to 300 gigahertz. And this lambda eventually, even if you're talking about visible light. The wavelengths are in the range of hundreds of nanometers, and your electron or your particle has dimensions of very they're very low dimensions, around 10 to the minus 15 for protons of the meter, or 10 to the minus 18 as upper limit. We suppose the electrons are point particles, but eventually for systems the spatial variations of the wave can be discarded. So that's why we can consider only the the time dependence of the field. Because this term here, if you are not at z equals to 0, just adds a phase here, a phase which is almost the same through the entire system of a spin half particle. All right, so we don't need the spatial variation for the wave. All right, so we will consider this case here, and using this situation, our system to be solved will be this one. The Hamiltonian would correspond to minus a Bohr magneton, some B0, which is a constant field in the z direction. So this produces the Pauli matrix in the z direction, minus a Bohr magneton, some B0. This amplitude is typically very weak when compared to the static field, so this scenario will apply eventually. And in this case, we have cos, the cosine function of omega t sigma x. All right. So this problem here has a time varying component, and when you have time varying problems, Hamiltonians of the form some h0 plus some time varying, some v of t here, some time varying operator. This is the constant, this is the time varying component. You can split your system into two parts. One which evolves with Schrödinger equation, and other parts with which evolves as a Heisenberg picture. And this is called the interaction picture, but we will not use this picture. I'll talk about later. In the interaction picture, your operators, so sigma of z, sigma of x, sigma y, rotates or evolves according to a Heisenberg picture, but using only this part. All right, all the operators evolve according to the non-varying part of the Hamiltonian, and all the states evolve like Schrödinger's picture, but only with this part of the Hamiltonian. So you split the time dependence. Some things, the operators vary according to Heisenberg, but considering only this part of the Hamiltonian, and the states evolve like Schrödinger's picture, but only considering this part of the Hamiltonian. This is the interaction picture. We'll talk, we'll use here Schrödinger's picture, all right? But in Sakurai, I mentioned that because in Sakurai he is using the interaction picture already. We'll not do that for now, all right? So what is the problem right now? This is the Hamiltonian of the system, all right? This is the Hamiltonian of the system. And what is the problem we want to calculate? Find the averages of sigma z sigma x, sigma y, the averages of the spin components. Well, I can put this to the end to make this sequence right. Z, Y, X, Y, and Z, the components of the Pauli matrices. I want to calculate the averages. And considering the initial state to be fundamental state, psi 0 is equal to the up state in the z direction. So this is the initial state, 1 and 0. This is the initial condition for the system. In the previous lecture, we considered a magnetic field along the z-axis and an initial state corresponding to an eigenstate along the x-axis. So field is constant and the spin rotated, which is called the spin precession problem. Here, if we did the previous problem considering that the initial state was not an eigenstate of the sigma x, but if we considered there this initial state, the state would be parallel to the field. It never changes. There is no precession because the state is already an eigenstate of the H0. But now we have initially the magnetic field applied to the z-axis, a spin state which corresponds to an up state, which is the lowest possible energy state, but there is a time varying field here perpendicular to the z-axis, and this time varying field will induce rotations, transitions between the up state and the down state by absorbing photons. So this state here is the lower state, the ground state of the system, but it can absorb a photon from the radiation field here, and it can go to the down state, which has a higher energy, and then it can release that photon and come back to the ground state, and it goes on forever and ever. And this problem with a continuous wave, this because this exists forever in time, it is called a continuous wave, a CW problem. Okay, this is a CW problem. Uh, the system absorbs photons and releases these photons later. All right, so it goes on forever and ever. This kind of oscillations are called Rabi oscillations, which will find out when we solve this problem. So Rabi oscillations will be part of the solution. All right, it corresponds to absorption, emission of photons in the problem. So we will try to find out these oscillations, solving this problem. All right, and for magnetic resonance, normally what is done, it's because the system has dissipation, it has losses. The system here is lossless, but in practice, for a collection of spins, they can collide and then can relax. The relaxation process allows to insert the radiation field, which has a frequency, but just for a certain amount of time. So it is turned on at time t equals to 0. This radiation field is turned on, so you inject a pulse of electromagnetic radiation into the system, and then you switch off the radiation. It endures for a certain amount of time. So you turn on here the field with amplitude B0. In practice, it is what is really done. And for some window in time, you insert the radiation, which is a cosine, so it oscillates here. You insert and then you switch off this radiation field. And this thing here, this time here in the magnetic resonance strategy, for instance, for MRI equipment, this time duration of the pulse, of the electromagnetic pulse, is properly designed in order to the system absorb photons, and when this is switched off, the system relaxes to the fundamental state, to the ground state. And you need to measure this re-emitted absorption, and that's what is really done. But right now, we are interested in considering continuous wave operations. The field is turned on by at time t minus infinity and is switched off at time t going to infinity. All right, it's never ceases to exist. In fact, it exists forever. So the oscillations, the Rabi oscillations, will happen forever. Right? It's the case of a lossless system, and it's easy to do the calculations, because if you insert some window in time here, problem complicates a little bit. This has a nice solution for the continuous wave oscillation. All right, and we will solve this system in the next lecture. All right, but for now, just to make things ready for the next lecture, where we'll solve this problem, we can define two things. Because the H0 here, the problem, the non-varying in time problem, corresponds to this thing here. Okay, this is the unperturbed Hamiltonian of the system. It doesn't change in time. The other part is time varying. We can already know that there are two states, the up state, which corresponds to the energy equals to this value here, right? And the down state corresponds to the energy, because the sigma z is the diagonal matrix, corresponds to this energy value. All right. So if you want to see what happens in an energy diagram, you have the down state, which is the higher level of energy, and the up state, which is the ground state of the system. And the energy difference here corresponds just to the energy of the upper state minus the energy of the down state. This delta of E here is the down state energy minus the up state, which is the excited state, minus the energy of the ground state, and it corresponds to twice this value here, twice this value here. Then, in order to produce transitions, as we will see, okay, effectively produce transitions, we need to insert photons with frequencies which we will call omega zero. I don't know if you can see here, omega zero corresponding to exactly twice the magneton, the Bohr magneton, which can be the nuclear magneton for protons or whatever, times the magnetic field B0. And notice that increasing the value of the magnetic field, the polarizing field, the constant field, you will find that the energy system splits more and more. All right, so this is a control parameter. You can just adjust the energy difference by varying the magnitude of this field. But once it's applied, it remains constant in time. All right. In the ideal world, this field exists forever, from minus infinity to infinity in time. But in practice, you can adjust the value of this constant, apply this non-varying field over long term, right? And now you can write this value of Bohr magneton times the B0 equals to h bar omega 0 divided by 2, because the energy difference is twice this value here, all right? Also, you can define another frequency here, which is some omega, which corresponds to twice Bohr magneton times B0. We do the same thing. This capital omega corresponds, or you can use another value here, but I will use this capital omega divided by the h bar. This here corresponds to a frequency as if there were no constant field here, and if your frequency goes to zero, you would have only a magnetic field in x direction. And notice that this frequency, the omega naught, the omega subindex 0 here, the omega naught, is just the frequency of rotation for the spins with respect to the field applied in the z direction. All right? This field in z is constant. And if you would consider an initial state in the x direction, this state would precess with this frequency here, this omega naught. But if you turn off this field in the z direction and you insert an x field, a field in the x direction with a frequency vanishingly small, it would be a constant, and the spins would precess around this x direction now, because it's just the same problem, it's just rotated. All right, but the frequency of rotation, if the frequency here, the omega here, goes to zero, the frequency of rotation now is this capital omega. All right, that's the problem we are willing to solve. And this way we have the Hamiltonian, which is of this form. The Hamiltonian of the system we want to solve has this form: minus h bar omega 0 divided by 2 sigma z minus h bar the capital omega divided by 2, all right, cosine of omega t sigma x. This is the problem we want to solve. All right, this is the Hamiltonian of the system, and problem is solve for psi of t considering the initial state is this one, the up state, the ground state of the system. This is the problem we want to solve. We want to solve this Hamiltonian considering this initial condition. Well, the initial condition has no big influence in the physical content of this theory. All right, but notice that it can be any two-level system, because any two-level system can be mapped can be put into correspondence with the spin half system. All right. So I'll finish it here. In the next lecture, we will solve this problem properly. All right. It is a little bit tricky for the first time when you see it, but we'll try to make it clear in the next lecture.